Yeah, Atul used to come, even he also not attended. Yeah. Yes, sir. Yes, you can start, I think.
Okay. So it's almost like 70, 80 slides. So let's go fast, as well as if you have any doubts in between, you can ask. Okay.
Yes. Yeah.
Okay, what's a stainless steel? Basically, I will introduce 2-3 slides about stainless steel and then the weldability, and then we'll start to directly the welding issues. Okay. So stainless steel, at least 10.5 chromium to make stainless. That means it will not form rust. It will not form any iron oxide, the rusting or the corrosion. When there is a minimum of 10.5% chromium in steel. So, and in stainless steel, iron content exceeds that of any other element. Iron content is the majority, like 70%, like that. Yeah, 60%, 60 to 70%. And carbon is usually less than 1.5%, because this is because to have the weldability. Okay. So now, what is the effect of adding chromium? The weight loss or the corrosion is drastically reduced. When you have more chromium, you have more corrosion. Whereas when you have less chromium, you have when you add chromium, then you have less corrosion. Simple as that. So the chromium gives the corrosion resistance. Okay. Okay. Now, pure iron at various temperature, you can see how when we melt the steel liquid, when we melt the iron, and then when it comes to the room temperature, what are all the transformation it takes? This is called allotropy of iron. Allotropy means iron exists at a different form at different temperatures. Okay. So it is liquid at 1540, and then uh, at 1400 roughly, it is again BCC, which is called delta ferrite, but this BCC is a bit slightly different. Okay. Then at around from 1400 to 912, it has a austenitic phase, and then at 912 below, it becomes again BCC, that is alpha ferrite. So this is called delta ferrite, and this is called alpha ferrite. So you need to remember this. In stainless steel, the ferrite what we see is mostly delta ferrite. Okay. In carbon steel and low alloy steel, the ferrite what we see is alpha ferrite. Okay. Now, carbon and alloying effects on iron. So sometimes what happens is this alpha ferrite is, I told you, this alpha ferrite is not in stainless steel, is because of the alloying additions. When you add more chromium and nickel, okay, you either have ferrite, or you have, that is ferritic stainless steel, or you have austenite, which is austenitic stainless steel, or you directly transform to martensite, which is martensitic stainless steel. You don't have a alpha ferrite. It is only in carbon and low alloy steel. Okay. Okay, so there are various elements which influences the property, because we add more of alloying elements in stainless steel. It influences the property. So for corrosion resistance, mainly chromium, nickel, phosphorus, and moly. Okay, you know that the iron pillar is made of iron pillar is mainly having phosphorus, and that is not corroding yet in India. So that is because the phosphorus has a corrosion resistance property. Then chromium and nickel moly induces corrosion resistance. Mechanical property, almost all elements contribute to mechanical property. High temperature resistance, again chrome, nickel, moly, and titanium and niobium. Okay, meshnability only sulfur and selenium. Okay, and phosphorus a bit. And weldability, almost carbon, chromium, everything will affect your weldability, whereas only manganese, moly, and titanium and niobium are beneficial or neutral. And that's it. So that's the important property. So main stainless steel families we have is austenitic stainless steel, which is non-magnetic, and non-magnetic means it is not magnetic. Okay, it has a it's diamagnetic, like no, it is not magnetic. It will, if you bring the magnet, it will not stick. And non-hardenable. Non-hardenable means you cannot harden by heat treatment. You can do a heat treatment and form martensite and then get a higher mechanical property. Cannot. We cannot do that with austenitic stainless steel. Okay, duplex stainless steel, which is magnetic, because of 50% ferrite is there, it is magnetic, but it is again also non-hardenable. That means you cannot do a heat treatment and make the properties higher. Okay, and martensitic, it is magnetic and hardenable. So you can, martensitic is magnetic because it is having a ferrite, and then 80% or 90% ferrite, and then this can be heat treated and then form martensite and then temper, so it is hardenable using the heat treatment. Whereas ferritic is again magnetic because of ferrite, and then it is non-hardenable again. It will not, if you do a heating or quenching, then it will not change the phase from ferrite to anything. Okay. Then there is a precipitation hardening stainless steel. There are two types. One is austenitic and austenitic precipitation hardening stainless steel and martensitic precipitation hardening stainless steel. We will not discuss much about the precipitation hardening because this is not used regularly in the industry, this material. Okay, we will talk more of these four items weldability. Okay, stainless steel. Okay, when you have a lower chromium, it is a normal ferritic steels like carbon steel and low alloy steel. As you add more chromium, straight chromium is 12% chrome. When you add 12% chrome, it becomes martensitic stainless steel. Okay, so from 12% up to 18% roughly, 12% up to 14%, only chromium is there and it is martensitic. But after 14%, you have to add a bit of nickel to make it, to remain it as a martensitic stainless steel. And after some 18%, if you add more chromium and even with nickel, it becomes a ferritic stainless steel. Okay, so this is how the balance of chemical composition results in the phases. Okay, and then in duplex stainless steel, you have lower nickel. Okay, from 5 to 10%, 5 to 9%. Okay, and then higher chromium, like 22 to 25, 27, like that. So this constitutes the region of duplex stainless steel. Nickel is from 5 to 9, and then chromium is from 22 to 27. Okay. And austenitic stainless steel, 18 chrome, 18 nickel is a very simple stainless steel. We all know. 188 is the 304 austenitic stainless steel. And then from there, variations are there, which we will discuss in the further slide. I'll have a dedicated one slide for austenitic stainless steel family. Precipitation hardening is like 17% chrome, 4% nickel, 17% chrome, 7% nickel. There are two categories. That constitutes the precipitation hardening stainless steel.
Okay.
So now we have completed the introduction. Yeah, yes, sir.
Yeah, sir, can you go back to the previous slide? Yeah. So martensitic and ferritic. So what is the, I mean, how they are different, like in terms of behavior or character?
Okay. I want to go for that one. I want to show this slide.
Yeah. Now we can see.
Okay. Now, if you see the iron chromium, this is called iron chromium diagram. So if you see the diagram, you can see that the region is like 11 to 13% roughly. You can see that it is transforming to gamma plus alpha. Okay, this gamma, this is where the region of martensitic stainless steel. So minimum we need 10.5 as a chromium. So when we add 10.5 as a chromium, around 11 to 13%, then this is the window where we have the gamma transforming to martensitic stainless steel. After that, it is purely ferritic stainless steel. So in order to expand this region, we need some amount of nickel to expand this loop, because nickel is again austenitic stabilizer. So to expand this loop, we need some amount of nickel. But that too also can be done to some extent only. After that, if you add more chromium, it becomes a ferritic stainless steel. Okay.
So we prefer to have martensitic is advantageous rather than ferritic. Ferritic means it behaves like
it depends upon what you want, because martensitic is used for high temperature application only. Okay. Because you have a low chromium, so you cannot expect a corrosion resistance like austenitic stainless steel or duplex stainless steel in chloride environment. So in chloride environment, generally we don't use martensitic stainless steel and all. Okay. Only where you want a moderate corrosion resistance but high strength, then that high strength means then you have a high strength and high temperature, and because of your chromium you don't have you have some corrosion resistance, but which is not a very good corrosion resistance, but some corrosion resistance.
Okay.
So this is the requirement. So in this requirement, in this case, we generally go for martensitic stainless steel. So that's why usually martensitic stainless steel is used in high temperature applications.
High temperature. Oh.
Or basically for pump impellers, like that.
So this 304, 316 will come under which type, sir? It is
austenitic stainless steel.
Austenitic. Okay, correct. It is austenitic stainless steel. Yes. Okay. Okay, sir.
So
okay. Go ahead, sir.
Let me. stop sharing once again and then.
Yeah.
So in simple term, the ease with which metals can be welded or fused without producing defects. This is called weldability. So now what we are going to see is not the welding process, but how we are avoiding defects and unwanted microstructure by knowing the background, knowing the theoretical knowledge, and then how we can weld properly and then achieve best mechanical property and good corrosion resistance. This is what we are going to learn. We are not going to learn about the process. Okay.
Yeah. Yes.
Okay. Now austenitic stainless steel. What are all the attributes of austenitic stainless steel? The austenitic stainless steel is typically 212 megapascal, which is equivalent to mild steel. Okay. Good low temperature impact properties. So, but that's why when your design temperature is up to minus 196, you go for austenitic stainless steel, and that is because of your FCC phase. That is austenite phase, which is FCC. This is austenite, which is face centered cubic phase. This, when you have a face centered cubic phase, any material like copper, aluminum, austenitic stainless steel, like that, you will always have a higher sub-zero temperature operating limit. Okay. When the moment when it comes to duplex or like a ferrite, the moment ferrite comes, then your MDMT will be restricted. That is, you can go up to minus 29 or minus 46 maximum. That's why duplex selection is minus 46, whereas austenitic stainless steel is minus 196. It's because of the austenite phase.
But duplex stainless steel, sir, I think we need to do impact testing always. I think. It becomes mandate. Always we need to do impact testing, right? I think below.
That is because you for minus 46. Anyway, even carbon steel and low steel, any material when minus 46, all ferritic steels are impact tested as per code.
No, there's some exemptions are there for plates. Generally, don't require impact testing as per code unless the thickness is very high. We can exempt, but whereas for a duplex stainless steel, if it's more than 10 mm, we need to mandatorily do the impact testing.
Yeah. There are some minor exceptions that is there. Yes. It's okay. But apart from that, generally for load, to guarantee a ferritic material at low temperature, we always need testing, because if there is a ferrite phase and we cannot believe that phase, it is not trustworthy.
Yes.
Okay.
Yes. So austenitic means it is good toughness property.
Trustworthy. Yeah. Even austenitic also, up to minus 110 only, it is minus 110 or 111 only, it is impact testing is not required. Even minus 196.
Minus 196, sir. Minus 196 for.
No, minus 196, they will need impact testing. Like they prefer impact testing.
No, sir. Up to minus 196, it is not required for 300 series.
Like for code, actually. For code.
As per code.
Some of the clients, they tell us to do testing at minus 196. Up to minus 110, they will say okay. But if it is directly minus 196, you go for a testing, impact testing. Just show the values.
Yes.
Okay. Just values and just show the lateral expansion in impact testing.
Correct. Yeah. In case of stainless steel, stainless steel, it is not energy, only lateral expansion.
Lateral expansion. Yeah. So strengthen significantly by cold working. Okay, we can do cold working, but many of the applications, they will restrict that you should not have any cold work. So this is not applicable, but it can be strengthened significantly by cold working. It is because the austenitic phase is having high toughness, so we can strengthen easily by cold working. Okay, it is ductile, it is tough, so we can do more cold working and then we can strengthen. Then more cold working we can strengthen. But this is not done for the equipments or vessels. We don't use a cold worker plates or pipes because it is restricted by the code and client. Good atmospheric and elevated temperature corrosion resistance. This is because of the fact that we discussed about the amount of chromium and nickel, 18% chromium, 8% nickel. So we have a good corrosion resistance. Weldable with proper precautions. Okay. Weldable means we can weld without any cracking or defects with proper precautions. Okay, this is a simple slide which shows the family of austenitic stainless steel. So 304 is the base, mother of all stainless steel. You have to, this is our Mata, Bhumi Mata, like this is our base stainless steel. Okay, from which everything comes up. All the things are coming up from 304 only. So from 304 you add moly 316 and you add more moly, that is up to 3%, 2 to 3% moly is 316 and 3 to 4% moly is 317. And then you lower the carbon. This is carbon is 0.08 in these cases, and then when you lower the carbon to 0.03, then it becomes L grade. Okay, from 304 8% chromium, you add just titanium, it becomes 321. You add niobium plus tantalum, it becomes 347, which is used for high temperature application in stabilized condition. Okay, then if you add sulfur and selenium, that becomes a machining, improve the machinability, machining stainless steel. Then you add more nickel and chromium, like 20 to 25% chromium and 20% nickel or something like that. Then it becomes like this high temperature grades, like 309, 310, 314, 330. And then further, if you add only nickel, that becomes a nickel based alloys. Okay. Then from 304, you lower the nickel because to improve the chloride SEC tendency. And then you have retained chromium. You increase the chromium, lower the nickel, then that becomes a duplex stainless steel. Okay. You lower the nickel and then.
Or super duplex. Super duplex also come in the same, right? I think.
Super duplex is again in the family of duplex. We call duplex super duplex. Yeah. Okay.
Super
then
duplex I think is 25% chromium, right?
Yes.
Yeah.
Okay.
Yeah.
Okay, the word super comes because when it is having a minimum PRN of greater than 40, then only it is super.
40, yeah,
not because of chromium.
Yeah.
It's because of the PRN value.
Yeah.
The word super is because of PRN. Okay?
Yeah.
Okay. Now, when you lower nickel, then add copper, titanium, and aluminum, this becomes a precipitation hardened stainless steel. Okay. Then you add manganese and nickel, this becomes a manganese stainless steel. That more of a manganese. Austenite is more with manganese. Yes. Okay. And nitrogen. Yeah. So this is a overall broad view of austenitic stainless steel family. So now weldability is, I told you what are the problems with the welding. Okay. Yeah. Weldability of austenitic stainless steel, what are all the problems we have? We have weld solidification cracking, intergranular corrosion in HISF, knife line attack, stress corrosion cracking, pitting and crevice corrosion. So we have so many problems because of welding. These problems we face, if you don't weld properly. So you need to properly weld to, get good corrosion resistance, to avoid cracking, etc. Okay, first we go for weld solidification cracking. This comes because of two reasons. One is you have either a high sulfur and phosphorus. Okay. Okay. You have a high sulfur and phosphorus, and then you need to have a proper phase balance, like proper chromium and nickel equivalent. Okay. So that results in proper solidification pattern, solidification mode, we call mode of solidification. Okay. So first I attack the solidification mode. The solidification mode should be, it should not be from austenite. It should not fully form austenite. From liquid directly, if it form austenite, there is a high chance of cracking. Then if it forms first austenite and then transform to ferrite and then it forms austenite, there is also a high chance of cracking. That I will tell you why. Later slide, I will tell you why that is happening. Then if you have a liquid weld metal, you have liquid. From there it forms ferrite and then it transforms to austenite. Then it has a high chance of not having any cracking, not having solidification cracking. So this happens when you are having a solidification, like when you are welding, immediately after welding, you will find the cracks in the center line. So this is called center line cracking or solidification cracking. You find cracks like this in center line. Okay. The reason is, one reason is you are either solidifying in the austenite mode or austenite ferrite mode. You are not solidifying in the ferrite austenite mode. Okay. So normally you would have seen that why they want always some 3 to 10% ferrite in weld metal. They would have told that you have a minimum ferrite number. Okay, 3 to 10 ferrite number in weld metal, that is required to prevent this type of cracking. Okay. Now, if you see the WRC Welding Research Council 1992 diagram, you can see that this 0, 2, 4 and all is ferrite number. Okay. And this side we have chromium equivalent, the elements which support chromium or which support ferrite stabilizer. And this side we have elements which support nickel or the austenite stabilizer. Okay. You have to balance the filler metal composition in such a fashion that you always end up in this ferrite to austenite region. Then only when you weld, you don't have cracking. Okay, otherwise you will end up in cracking. If you end up here or here, you will end up A or AF mode, you will have cracking. When you end up in FA mode, you will not have cracking. Or when you even end up in F mode, you will not have cracking. So a normal thumb rule is the chromium equivalent to nickel equivalent shall be 1.5. It should be 1.5 and above. Okay. So the simple estimation of ferrite number estimation we can do 316 grade I am taking dash 60. Okay. And then I am taking the chromium, approximate chromium and nickel composition. Based on that, I am calculating the chromium equivalent to nickel equivalent. And then if I pose it in this diagram, you can see that it is falling in the FA region. So that means this will not crack when I weld. This will not undergo solidification cracking when I weld. Okay?
Yes.
So typically I told that chromium equivalent to nickel equivalent is usually you need a minimum 1.5. To design consumable, or consumable should have such that the chromium equivalent to nickel equivalent should be 1.5, so that if you end up in austenite mode or austenite ferrite mode, you will have a greater cracking susceptibility. But the more you become like a ferrite mode, the cracking susceptibility totally reduces. Okay, so that's why any minimum 3 to 10 ferrite number you need to have in weld metal.
Yes.
Okay, so now what is the problem? Why is it so? Why we need some amount of ferrite? Why we need some amount of ferrite?
Yeah.
Hello? Yeah. So basically, why we need is this impurity content certain phosphorus in the consumable or in this base material, basically, which contributes to the melting in the weld pool. Basically, you have more solubility of this sulfur and phosphorus in delta ferrite, and you have poor solubility of sulfur and phosphorus in austenite.
Okay.
The sulfur and phosphorus is more soluble in delta ferrite and less soluble in austenite. And the sulfur and phosphorus are having lower melting temperature. They will solidify in the last. They will have lost solidification. Okay, they will remain liquid till 900 degrees C. Okay, and when the weld is solidifying, what will happen? This will be the place where last solidification is happening. Okay. Now, when the weld is solidifying, it will shrink. There will be a shrinkage. Okay.
Yeah.
Okay. Now, if any sulfur and phosphorus is there and it is in the liquid phase at 900 degrees C, this will shrink and this will pull from here. In this direction and this direction, due to the shrinkage, means solidification, it will pull. The weld will pull. Okay. Now, if the sulfur and phosphorus is in liquid stage, it will end up in cracking. Okay. In order to avoid that, what we do, we send the sulfur and phosphorus inside the delta ferrite. If you have ferrite, you send the sulfur and phosphorus soluble in delta ferrite, so that you don't have sulfur and phosphorus free in the weld pool, which will remain as a liquid at 900 degrees C. Okay. So this is Sutala diagram for base material usually. So typically that 1.5 chromium equivalent to nickel equivalent balance is very important. So above this line there is no cracking. Okay. And when the phosphorus and sulfurant is extremely low, there is no cracking. Okay. When the phosphorus and sulfur in the consumable is extremely low, there is no cracking. So that's why in your consumable you always restrict phosphorus and sulfur very low.
Yes.
If you see. Okay. Yeah. Otherwise, if you have a higher phosphorus and sulfur, you should have the chromium equivalent and nickel equivalent minimum 1.5, such that you end up in ferrite austenite mode. Okay. You should have a higher ferrite number in weld. Okay. So lower chromium and nickel means the solidification mode transforms to either austenite or austenite ferrite.
Austenite, yeah.
So then automatically you end up in cracking. Okay. Now you have a modified Sutala diagram, which is for rapid solidification conditions. That is arc welding, which is a normal process. You have this chromium equivalent to nickel equivalent. You can maintain 1.4 or 1.5 at the borderline. But for a process which has a high heat input and high cooling, high solidification, means faster cooling, you need to have a higher chromium equivalent to nickel equivalent. Okay. Because what happens is, the faster cooling means your the alloying element movement is restricted. Sulfur and phosphorus will not move, will not diffuse and then go in ferrite phase easily.
Yeah.
So what you need to do is, you need to increase the ferrite content so that higher you understand, sir? Higher heat input means faster cooling rate. Faster cooling means diffusion is less. Okay, in that case, you need to have more ferrite so that you will have you will facilitate sulfur and phosphorus to go in ferrite wherever it is available nearby.
Nearby. Okay. Okay.
Okay.
So means
If you have a less, if you have less ferrite, it means it has to be search the ferrite and go and enter, go and get solidified. I mean soluble. But if you have more ferrite, then it is soluble easily.
yes.
So only for the high heating process, we need to have more chromium and nickel equivalent.
Yeah.
Okay, prevention of weld solidification cracking, as we discussed, composition control, chromium equivalent to nickel equivalent, FS solidification mode in WRC 9299 is in FA mode. We need to have FA mode. That means you should have some amount of ferrite in your filler metal. Most of the people know that they need to have 3 to 20 or 3 to 10 ferrite number, but they don't know why. Most of the people. Okay.
Okay.
Really, if you ask sir the reason behind them, they don't know this.
Yeah.
Everyone will know that there is a 3 to 10 requirement, but the reason behind that they don't know.
Yeah.
And then reduce impurity. Of course, if you have low sulfur and phosphorus, we have seen the graph, Sutala diagram, that there are reduced sulfur and phosphorus in the consumable as well as in the base material. You don't have cracking. But if you have more phosphorus and sulfur, you need to have more ferrite in the weld metal.
Yeah.
And also minimize the weld restraint. Okay. If you have a very high depth weld and a low width, then there is a chance of solidification cracking. It is nothing to do with the chemical composition of this one. It is due to the joint restraint, because of which the cracking happens.
Okay. Like
So you
sometimes.
have you have to have a wide. Yeah.
Yes.
Tell me, sir, please.
No, because sometimes I have seen some companies to save that weld metal, they will reduce the weld angle. I think they will limit it. So,
Yeah. Narrow groove welding they call.
Narrow groove welding.
So coming to the corrosion aspects. So far so good. So far how it is going?
Yes. Yes, sir.
Yeah. Good.
All good, sir.
Okay, sir.
Okay. Corrosion, thank you. Corrosion in austenitic stainless steel, we have, I told, many forms of corrosion like stainless SCC, pitting, crevice, intergranular erosion corrosion, and MIC. We will see mainly intergranular corrosion and pitting and crevice corrosion and SCC. Okay, these are all the prominent corrosion problems we face in austenitic stainless steel material selection. Intergranular corrosion in HIZ, austenitic stainless steel, when exposed to the temperature of 425 to 800 to 400, okay, they become susceptible to intergranular attack. The thing is that they form chromium carbide in the boundary, and then the carbon combines the chromium and form chromium carbide, which is called sensitization. Okay, so now what happens is, this is a normal microstructure, annealed microstructure. Okay, now this is your a normal microstructure will have a grain boundary like this. But what happens is, when you cool slowly from 800 to 400, or when you heat it slowly from 400 to 800, this chromium in the middle, carbon in the middle and the chromium near the grain boundary combines and then form chromium carbide, Cr23C6 forms. And then the grain boundary becomes like this black. This is called Cr23C6 chromium carbide precipitated sensitized structure we call. Okay. Okay, and why this phase is not preferable? Because if you see, you take one grain boundary, this region. Okay, this region you take. This is this line. Okay, and then if you see the chromium, because the entire grain boundary, the chromium concentration, the chromium is taken away by the entire boundary. Near the boundary, the chromium concentration is very high. So in the boundary region, the chromium concentration is very high. So from the black color precipitate to this one to this region, this one to this region, there is a problem, because all the chromium from here has gone in this chromium carbide precipitation. So the chromium here in this region is low. It is below 12.8%. This is near the precipitate, it is below 12.8%. That means it is a normal stainless steel. This is a chromium depleted zone. Okay. I am just replicating this one grain boundary. I am just extrapolating and then showing you that how chromium is rich in the grain boundary, but adjacent to the grain boundary, the chromium is depleted. All this chromium from this region gone to this region.
Okay.
So the chromium is depleted. Yeah.
Chromium will deplete from the central region of the grain
and go to the boundary.
Because it is attracted by the chromium carbide.
No, right? Because of the diffusion facilitated at the 400 to 800 degrees C, the thermodynamically and kinetically they are stable and they form the chromium carbide.
Okay, chromium carbide. Okay. Okay.
The thermodynamically,
because of this, I mean, if we don't do rapid cooling, I think this will happen, right?
Yes, correct.
Right,
absolutely.
Yes.
So, carbon, we have seen that carbon is having a profound influence on susceptibility to IGC. When you have 0.08% carbon, even when you cool it from 900 to 400 degrees C, even within, if you cool, you have to cool less than 10 seconds, like less than 30 seconds. Otherwise, you have a chance to form chromium carbide. You have to cool very, very fast. Otherwise, you have a chance to form chromium carbide. But whereas when you have a carbon content less than 0.03, okay, you can cool slowly in air or even 100 hours. Like 10 hours you can take. 0.03, 10 hours you can take to cool. And if it is 0.02 or 0.019, then you can take 100 hours. So basically, when you reduce the carbon, you can cool slowly between 800 to 400.
Yeah,
okay. When you have high carbon, then you don't have the luxury. You have to cool very fast. Okay, that's why all the filler metal, all the things, when weldability is involved, all the base material and filler metal are chosen with L grade. This is the reason. Okay.
Sir, then can you go back to the previous slide? One more slide where you show the grain. No? This chromium carbide form. So then, how it will contribute to the corrosion? Can you explain?
No,
that is because
basically the corrosion resistance is contributed by the greater than 12% chromium. When
12%
I told you the first one. Yeah, but if you see near the grain boundary, what is the corrosion you have seen? Less than 12.8%. This is this is like a 5.8%, 6.8% like that here. Near the this is like a typical low alloy steel or typical low carbon steel.
Low carbon,
without chromium or low alloy steel with very limited, less amount of chromium. So if you do this way, if you have this region in a stainless steel, then you are undergoing corrosion, right? It will have intergranular corrosion.
Correct. Okay, sir. My next question is, to prevent it, we need to do it rapid cooling, provided if the carbon content is higher. Suppose if you take 304 material of 316 where the carbon content is high, like 0.08. Okay. Yes, sir.
Yeah, that is coming in the next slides. Yeah.
Okay.
One of the ways of prevention is that one.
Yes.
Okay. So section of pipe, you can see that in the weld, exactly the adjacent region where there is a region, HIZ region usually. This is weld, this is base material, this is exactly HIZ region where there is a chromium carbide precipitation has happened. And the inside there is a corrosive fluid that has exactly corroded only the HIZ. Because there is a chromium carbide precipitation. Okay, if you see that this region is okay, all no chromium carbide, but this is a region where chromium carbide, you can see that it is a totally intergranular corrosion. If you see that, totally a grain, intergranular, all grains have been taken away. Okay. Okay. Now comes your remedy. Okay, remedy for sensitization. I think we are going very slow. 9:30. I think we have to complete by 7:30, right? Only one. No, I have not finished even austenitic.
If you told us, then we would add that time. You didn't inform us.
Otherwise, we can extend to next week also if okay for us, because this is a wide topic, sir. This is a 4 stainless steel we have to cover, and it's a very good topic. So I mean, I have put my heart and soul in preparation of this one, but the participants disappointed me a lot.
We can put in next week also if you are okay.
Okay, let's see. Okay. So remedy for sensitization: choose low carbon base metal, like as we discussed, Ramakrishna sir and Mohit. Select which is 0.03% carbon, so that you have a more luxury of this time. you can cool slowly, and then you don't end up in forming chromium carbide. Okay, only the chromium carbide will form after this curve. So till this point chromium carbide will not form. That means almost like you have 8 hours or 9 hours to cooling. Okay, and choose base metal stabilized with titanium or niobium such as 321 or 347. After welding, heat weldment to 1040 and dissolve carbides and then water quench. But this is in a bigger component like a vessel. How you can take the vessel and weld and quench? It's not possible, right? Yeah. So we either resort to low carbon stainless steel filler wire, and for high temperature application we follow 321 or 347. And only in the 321 or 347 there is one specialized form of attack called knife line attack. The 321 and 347 we buy in stabilized condition, like you will have a stabilization heat treatment added to the solution annealed condition, right? There will be 875 to 925 4 hours. You will add another heat treatment to solution annealing. Either first you do 1040 1 hour and then quench. After that you have to do a stabilization heat treatment called 875 to 925 4 hours or 2 to 4 hours. Okay, that's a stabilization heat treatment specifically for 321 and 347 grades to precipitate titanium carbide or niobium carbide. Okay, but what happens when you weld the region adjacent to the weld? This is the weld metal, this is the parametal. The region adjacent to the weld, it reaches so high that all the titanium carbide and niobium carbide formed goes into solution again. Okay, and then this is like a 304 again. This is like a plain 304 only in this region, small region. It is like a knife cut, This is HIZ, this is weld metal, and this is like a knife cut. Okay, thin region. So this is called knife line attack. That's because the region adjacent to the weld undergoes and reaches a high temperature like 1100 or 1100 degrees C. That this region, all the chromium carbide and titanium carbide dissolves. So this region is having chromium carbide, titanium carbide. This region it is dissolved. So when you expose to corrosive region, then this is forming a chromium carbide. Sorry, this region is forming a chromium carbide which undergoes again corrosion. So this is called a knife line attack. Okay. So what happens is you have a weld zone, you have a base material, and you have a sensitized region because of the high temperature reached over there. All the titanium carbide and niobium carbide goes into the solution, and then while cooling it forms chromium carbide. Okay, so basically what they do is they cool faster, and then they do for stabilized grade only. When you weld a stabilized grade, you try to do a stabilization treatment after welding if possible. Okay. Yeah. Otherwise follow the precaution of fast cooling, okay, after welding. So you don't end up in chromium carbide formation. Okay, so then we come to stress corrosion cracking. We discussed two. One is intercanal corrosion, one is knife line attack. The third one is stress corrosion cracking. Particularly in chloride bearing environment, the austenitic stainless steel undergoes stress corrosion cracking. The problem is because of the nickel is 8 to 12% in austenitic stainless steel. This is Cobson curve. Where the nickel is 8 to 12%, typically Cobson, one scientist tested that the material is having poor SEC resistance. When you lower the nickel, the SEC resistance is improving. When you increase the nickel, the SEC resistance has improved again. So only in a particular region, the SEC resistance is very low in magnesium chloride solution for austenitic stainless steel. So basically, the lower nickel is nothing but your duplex, and the higher nickel is about your nickel base alloys, like 625 and all. 625 is virtually immune to chloride SEC. And your lower nickel, which is duplex stainless steel, like 5 to 7 nickel, is also having superior chloride SEC resistance, chloride stress corrosion cracking resistance, okay, because of this concept. Okay, and this is the basic reason for the birth of duplex stainless steel. They improved the chloride SEC resistance compared to austenitic stainless steel by reducing the nickel. Okay, once they reduce the nickel, they added nitrogen. So you have a two combination, nickel plus nitrogen one side, and then chromium and moly in the other side. So you have one ferrite stabilizer one side and austenite stabilizer. So you get 50-50 phase balance. So you get duplex stainless steel, dual phase stainless steel. Okay.
Okay.
Okay. So for stress corrosion cracking, you need to have three environment. One is tensile stress, one is corrosive environment, and one is susceptible material. Austenitic stainless steel is a susceptible material. Tensile stress we have, and corrosive environment is that chloride bearing, any chloride bearing environment. Okay. If you have service, any piping, if you apply pressure, that is your tensile stress. Internal pressure when you apply, that is your tensile stress. And normal corrosive environment with any solution with the chloride, and then any material that is 304, 316 material which is susceptible to stress corrosion cracking. Then when all the three criteria is satisfied, then SCC will occur. Normal atmospheric storage tanks which don't have any pressure and which don't have any stress except weld residual stresses, if they don't have any stresses, then they don't undergo SCC. For SCC, you need to have stress, applied stress or residual level. Okay, applied stress plus residual stress, only applied stress or residual stress. Any of the three should exceed, we don't have any stress. So, one of the criteria is not there. If you cut any one of the criteria, then you don't end up in SCC. So that's why most of the time what we do is we end up in material selection, proper material selection. Okay, we do proper material selection to avoid chloride SCC because we cannot avoid tensile stress in service. We cannot avoid the chloride corrosive environment. Okay, so we select the resistant material. So you can have both. This is intragranular corrosion, intragranular SCC. Okay, okay. You can have a transgranular SCC. Transgranular means that it will cut the grains. Intragranular means it will pass through the grains. Okay, and there is a mixed mode also. It will have both cutting the grain as well as passing through the grain boundary. So SCC remedies, proper alloy selection, that is duplex, nickel base or ferritic, based on the level of chloride, temperature, etc., etc. Now it is more well established that we can select a proper material. PWC to eliminate stress, but this is seldom carried out in SS because it results in sensitization. So generally PWC is not carried out. This is just written for a theoretical purpose, but this is not applicable. We have to overcome SCC with proper alloy selection. Okay. Now pitting and crevice corrosion. When chloride environments like halide elements like chloride, bromide or iodide in aqueous solution, increasing temperature and microbes all causes, or any of this condition like increased chloride or increasing temperature, or there is a presence of microbe, all causes pitting and crevice corrosion in your stainless steel. Chromium oxide layer penetration, metal below the layer becomes active. So now in any stainless steel, the corrosion resistance is because of the chromium oxide. We increase chromium about 12% or 18% we keep in austenitic stainless steel. That forms a very nanometric level, nanometer level chromium oxide layer. Okay, that chromium oxide basically gives the corrosion resistance. Now the problem is when you have chloride in the this thing, the chromium punctures the chromium oxide layer, the protection layer or the passivating layer. Then it goes below that chromium oxide layer and then it attacks the base material. Okay, so that is why when you have chloride, this chromium oxide layer or the passivating layer is not fully functional. Chloride punctures the passivating layer and then it disturbs the passivity and it makes the metal active and it corrodes the material. Okay, so these are all one typical example of pitting and localized corrosion caused in austenitic stainless steel. The remedies for pitting is basically increase chromium, increase moly, increase nitrogen. As we would have come across a very common term called pitting resistance number, pitting resistance equivalent number. So this is chrome plus 3.3 moly plus nitrogen. So basically if you increase in chromium, increase moly, increase nitrogen, then automatically your PRN increases. If your PRN increases, your pitting resistance increases, then automatically you will not have pitting. So molybdenum bearing austenitics, if you see, there are a lot of, if you see, the effect is, if you have 16% chromium, the chromium is 16. Okay. If your moly is 3, so it is 3.3 times multiplied. So 3.3 into 3 is become 9. So moly is also very good. If you add even moly in lower content, then it has multiplied by 3.3 times. So it gives very good pitting resistance. Moly increases the pitting resistance. And then if you have nitrogen, it is multiplied by 16 times. That means nitrogen is contributing very much to controlling pitting corrosion or giving resistance to pitting corrosion. Okay, so you can add moly or nitrogen, I mean in a minimum level, that will be multiplied by 6, that will give maximum effect, maximum resistance to pitting. So we have common molybdenum grades which we use. Instead of 304, we use 316 or 317. And then you have 6 moly grades like this 254 SMO and AL6XN, or the 6 moly grades which we use typically, which is very good, and 2000 ppm of nitrogen. These are all called super because again the PREN for this pitting resistance equal number for these stainless steels are greater than 40. That's why they are called super. The word super in stainless steel will come only when pitting resistance equal number is greater than 40. Okay, now we to ascertain the pitting, how to ascertain the pitting in a laboratory test, we have a G48 method A, that is 6% ferric chloride in water. We will use this. Ferric chloride is very corrosive because this is an oxidizing solution. So we have some start from 20 degree and then increase 2.5, 2.5, 2.5, expose for 72 hours, look for pits or gauge the weight loss. The moment, from you start from 20, but after 35, it is getting, you can see the pits. That means it is, the critical pitting temperature is 35 degrees C. Okay, in 6% ferric chloride. Okay. So this is again the same test, CPT, critical, that's what I told, critical pitting temperature. So highest temperature at which no pits occur or lowest temperature at which pit occurs. So it is called the critical pitting temperature. I explained just now.
Yeah.
Okay. So this one more thing we need to see, that basically a material which is having a molybdenum of 4.3, 6.5 and 9, when you do a welding in the weld metal, okay, the moly observed is 2.3, 4.4 and 4.4. There is a segregation. There is a dilution. There is a segregation. So basically, if you are welding a 6.5 material with 6.5 moly, actually in the weld you get only 4.4. So basically you have to overmatch the filler wire sometimes. Okay, this is very important to have the same level of pitting in the weld. That's why they will say that base material is not pitting, sir, but only weld is pitting, sir. That is because in the weld you have lesser moly. Okay, in the base material you have a higher moly. In this case, you need to overmatch the filler wire. So for highest corrosion resistance in high moly fully austenitic stainless steel, overmatch molybdenum with 625 or C22. Sometimes we need to do this. Sometimes when you face problem of pitting in welds, you need to overmatch, because if you observe the moly in the weld, it is lower than the moly what we have in base material. Okay, when Ramakrishna sir, when you come across this problem, just check the moly. Okay, when they report only weld is pitting, base material is not pitting, just check this and you will have this problem.
Okay.
In such cases, we need to overmatch the filler wire a bit, put more moly in the weld to have a superior corrosion resistance. Also, so this is about cleaning after welding. So welding, again the corrosion resistance of the weld is caused by the chromium oxide layer. So this is not showing the chromium oxide layer. This is the oxidized layer, oxide layer, not a chromium oxide layer. If you don't clean and put it in service, you will get pits like this. So you have to clean it and remove all these weld oxides, all these oxide layer, and put a clean material after pickling and passivation. Then you will have a best corrosion resistance. Okay, so cleaning also plays a vital role in enhancing the corrosion resistance of the stainless steel. Okay, that's very important. Okay, so we stop here. We continue next week, sir. Do you mind?
Yeah. If you have any
Because I have
question,
to take another 3 stainless steel. If I have only completed austenitic, I have to go for duplex, then modern city and ferritic.
yeah. Any questions or any issues anybody want to ask, they can ask. So we'll.
Yeah, we can have an open discussion.
Oh, okay. So Ramakrishna or Mohit, anything to be asked?
No, I'm good. Yeah, wherever I had questions, I asked.
Okay, there itself you asked. Okay, Mohit.
And I think yeah.
Mohit, you have anything?
No, sir. Actually, I had very limited knowledge about this, but now I think I have understood very much about the weldability and stuff.
Yeah. Also, this weldability and that one way static way normal not enter much. But after this presentation, we came to know that there's many things are there to be taken care in this weldability and that one.
Yes. The presentation was really nice. Actually, the depth of knowledge is good. Like
Yeah,
the
very.
efforts you have taken, it's completely visible.
Okay. Mm-hmm.
Okay, first thing. Second thing is that while the first is the preheat you control, or the interpass also you control. You lower it so that it cools faster, and then
Okay.
weld the smaller bits. Weld the smaller bits for the higher grades, high carbon grades. Weld the smaller bits so that you will have a lower heat input. Then the cooling rate will be faster.
Okay. So that welding process we need to select such that your cooling rate will be faster.
Faster, yeah. Yes. One is intrapass you should not maintain. Interpass also it should be like a close to room temperature of 50 degrees C or like that. It is better. And then smaller bits, weld the smaller bits so that you will end up in for having a faster cooling rate, and then you don't have the sufficient time for the 800 to 400 transformation.
Okay. So means between pass to pass they have to give a gap. Such.
Yeah. And smaller passes, smaller.
Yeah. To cool down, how much time it will take to cool down?
No, it will cool down. It will cool down faster.
Okay.
I myself have seen that welding 1 meter. By the time I started, and then by the time reaching half meter, the point of starting is already cold. The starting 1 meter coupon, when I'm welding, when I'm welding a low heat input and then at the room temperature, by crossing 300 or 400 meters, when I touch the starting point, it is already cooled.
Okay, sir. Clear. Yeah.
Yeah.
Thank you, sir. Thank you so much.
Yeah.
Thank you, sir. Thank you very much.